Welcome everyone. So today we are here to listen to the second in the series of Samvaad talks in this under the SIG automotive theme, and it is my pleasure to introduce today's speaker, Dr. Ramesh. Let me just say a few words about him, his biography. So Ramesh has been with General Motors Global R&D in Warren, USA, where he currently holds the position of Senior Technical Fellow and Thrust Area Lead for Model-Based Embedded Software. At General Motors, he is responsible for providing technical leadership for research and development in several areas related to electronics, control, and software processes, methods, and tools. Earlier, he was in India Science Lab, General Motors R&D, serving as the lab group manager for two research groups on software and system verification and validation. During this time, he led several projects on next generation rigorous verification and testing methods for control software. His broad area of interests are rigorous software engineering, embedded systems, real-time systems, and more recently focused on AI and safety in automotive systems. He is the author of several patents and has published more than 100 papers in peer-reviewed international journals and conferences. He is an active member of many automotive standards committees of SAI and ISO. Prior to joining General Motors R&D, he was on the faculty of Department of Computer Science and Engineering at IIT Bombay for more than 15 years. At IIT Bombay, he played a major role in setting up a national center for formal design and verification of software. As the founding head of this center, he carried out many projects on verification of embedded software for several government organizations. He is a fellow of Indian National Academy of Engineering and was visiting an adjunct faculty of many institutions, IIIT-B inclusive. Ramesh earned his BE degree in Electronics and Communication Engineering from Indian Institute of Science, Bangalore, and his PhD degree in Computer Science and Engineering from Indian Institute of Technology, Bombay, India. So that's what I read out from his biography. Let me add a word or two from my own side. I have known Dr. Ramesh for more than a decade now. He was my manager at General Motors R&D, a very scholarly and lovable person, I would say. And the fact that we have not been formally professionally connected has not come in our way of being in touch for such a long time. And not just me, but all the people in our General Motors research lab are still very much in touch with each other and him. And I think Ramesh is the binding factor between all of us. So that's Dr. Ramesh. Welcome, Ramesh, to present this talk. And Ramesh is going to talk about software-defined vehicles, safety and verification challenges and solutions. So Ramesh, over to you.
Thank you very much, Professor Chakravarti. I think it has been a pleasure being associated with you, and thank you very much for this invitation to be part of this special interest group, and then providing some of my views and opinions on where the automotive industry is going as far as verification and validations. It has been a pleasure being associated with Mr. Chakravarti and also the other people that whom I have worked with in our Bangalore center. So let me start. I hope that everybody can see my slide, and so I have slightly revised my title. So what I'm going to highlight on the kind of multidimensional evolutions that automotive ECS, by ECS I mean that electronics and control systems, focusing on the V and V challenges, and possibly providing some solutions in the time frame. Let me move to the next slide. Right. There's a kind of general disclaimer I always keep in my slides. These are my own observations and opinion, not that of GM. Tried my best to quote the original source of diagrams wherever possible. And you can see two icons at the bottom. I think this is also a general disclaimer that I would like to say is that, one is, it's a kind of broad brush and a fine brush. Now, whenever we present things, we look at our contributions, our work, our area with a kind of fine brush, whereas the rest of the areas are kind of broad brush. And I think every presentation has this problem that mine is not any exceptions. Feel free to reach out to me at the end of the talk. Maybe we could also have some questions on that in case you have. So this is another thing that I have a kind of talk highlights. These are the things that I'm going to focus on in my presentation. Automotive ECS systems are undergoing, in my opinion, fundamental transformations along several dimensions, many of which, so people, you might have heard of. Propulsion system, from internal combustion engine, people are talking about electric vehicles. And in the feature space, what they call automotive ACE levels of automation, 3+ features are being introduced in automotive. Hardware architecture, also a lot of advancements and evolutions are taking place. Software architecture, some of you might have heard the term that software-defined vehicle, some of which I will highlight. Control algorithm development, again, there are changes from physics-based development or algorithms to more of data-based algorithms. And we are, even in the kind of design and development methodologies, there are changes like we are going agile, continuous improvement and deployment, over-the-air update. These are some of the keywords that some of you might have heard of. All these things, my focus has been on verification and validation. How these evolution changes pose challenges to the validation. And I will highlight some of the standards and guidelines in which I have been participating in the last 2 years. I think this is the talk highlight. Let me go and elaborate. So I think the journey from internal combustion engine to EV, from the kind of energy efficiency point of view, that this is the kind of change that is taking place. In fact, in the last 3 to 4 years, almost all the OEMs have announced that they are going fully electric. So the EV is redefined, from our point of view, EV is redefined the computation needs in automobiles. There's a whole lot of battery management system for safety and efficiency. Some of the important considerations that are happening: infotainment, connectivity, and autonomous driving, right? All these things are being served by or contributed to by going fully electric. So in the hardware architecture, so I think GM is probably one of the first companies to introduce microcontroller-based systems. Their electronic spark timing is timing control was probably one of the earliest one, electronics being introduced into vehicles. But today, with high-end cars being there, advanced driver assist systems and autonomous driving, so there are more than 100 ECUs, as they are called. They are simple, micro to mini to so major control units. They are controlling the different parts of computing different functionalities. And then you have more than 100 million lines of code in today's software, and multiple tens of networks connecting these ECUs and so on. So, and the evolution that is happening is that from 100 ECUs, they are trying to do highly integrated, thanks to the advancement of hardware, system on chips, so with 2 to 3 centralized compute platforms are being enabling, these multi-domain integrations that are happening in today's vehicles. this is another evolution that need to be taken into account, because the way in which software would be architected becomes quite different when you move from highly distributed architecture to centralized one. Right, as I said, this hardware evolution also is triggering the software architecture evolution. So we are going in a kind of big cycle. Now we started with centralized architecture, that's becoming distributed, and then again becoming back to centralized architecture. So automotive software, people have been talking about middleware based architecture. So you might have heard of terms like AutoSAR, which is a middleware platform or middleware architecture, as you can call it. Now, from classic to adaptive AutoSAR, I think that is one evolution that took place. And the more recent one is this Altify. I think GM has, for example, as a software platform called Altify. So essentially triggered by the various developments that take place in the smartphone industries. Even software in tomorrow's vehicles are going to be app-based. Altify is, for example, a platform introduced by GM for external suppliers and also for internal development to architect software as a kind of collection of apps on running on these platforms. Even the internal services could be like app-based and so on. So this is a kind of a preview of what is yet to come. So the way in which software is going to be architected will be quite different going forward. Instead of building softwares for individual controllers, creating builds for those individual controllers, and then connecting them together right when the vehicle is being rolled out of the factory, and after which the software never changes, we are going into this platform-based architectures, and the software will be evolving continuously. Right? I think that is triggering the way in which systems are going to be architected. Another dimensions that I would like to highlight is this in the feature dimensions, or the feature space, as I would like to call it. SAE has defined, on the right-hand side, you can see a table. So it's a well-known table in the industry. Levels of automation, increasing degrees of automations from no automation, which is level 0, to level 5, which is a kind of full automation. So essentially, degrees of automation increases, and then human role keeps decreasing. There are many new concepts that are coming into this domain, like operational design domain, the domain in which the vehicle is expected to operate. What are the driving tasks that the automation is responsible for? What is the kind of protocol between the vehicle and the human? And level 2 to 5 is essentially increasing range of ODTs and DDTs, as they are called. Level 5 is unlimited operational design domain, and probably beyond all DDTs. It will have to even check for the availability of gas, or charge in the battery, and tire pressures, and so on. So industry focus has been primarily on level 2 to 4. Right, I think in case of GM, so GM is also in this journey. Every industry is in this. Every automotive OEMs are in this journey, and GM, and I would like to call it as a kind of different variations of cruises. So we had adaptive cruise control, then that gave rise to super cruise, and super cruise to ultra cruise is a kind of this is a new features that GM is introducing soon in the market. And already those who are living in the California regions might have seen that cruise automation, which is a kind of company supported, it's a kind of joint venture with GM, running robo taxis, and the California transport company, transport organization has already given approval for running these vehicles. So this journey to fully automated vehicle is on, and it's a kind of matter of time that when they might be fully in deployment. Right, I think super cruise is is one of the features that are already in the market. Many of the people, for example, Professor Chakrabarti was mentioning that some of us actually were involved in the feature in verification and validation of this feature. So this has several long-range radars and front cameras and ultrasonic sensors, different kinds of features that are integrated together, like forward collision alert, lane departure warning, keeping the vehicle within the lane. So there are two important features that are essentially following the vehicle in a particular lane, within the lane, and then avoiding collisions and so on. So essentially, it's a kind of integration of active safety and automated steering and lane following features. So level 2+ features essentially shifting the functionality, software functionality from traditional control system paradigm, what they call as sensing, controlling, and then actuation, to a more like a robotic paradigm. Perception is becoming more important. Perceiving the road condition, perceiving the situation, accordingly planning, and then acting. So essentially, slowly it is becoming more and more automated. And perceptions and planning, I think, AI machine learning, like many other domains, AI machine learning is also playing an important role, like detecting lanes, traffic signals, various 3D object classifications, and then planning paths and so on. So AI machine learning is playing an important role. So as I said, evolution in the software development. So you might see on the right-hand side the V cycle of development. Very well known in the automotive industry. It's giving way to more agile development, which has become a kind of commonplace in several software industries. Automotive software development is also not an exception. So there is a kind of, people are talking about evolving software beyond the initial release. That is thanks to the connectivity platforms that are available in today's vehicle. You can flash new software, updates to software over the air. Over the air or OTA updates is becoming commonplace. Continuous improvement and continuous deployment. So as a result, automotive software systems are becoming complex and open, right? I think this has fundamentally changed the way in which software is being developed. Till now, software is being developed fully within the organizations, and then once the builds are integrated and validated, software was never changing. But this picture is slowly changing. Even today, some of the recent releases, so every quarter there could be new releases to the software, and over-the-air updates have become commonplace. But of course, these pose some challenges like unknown, unsafe situations that might arise because of updates to your software. Right. I think another trend that I would like to highlight on is from real to virtualization. So this is another trend that I see, that extensive modeling and assets for development and validation. Right. So you have models for the plant, vehicle dynamics models is something known, engines, motors, and batteries. Extensive sensor modeling, camera, radar, LiDAR. These are common sensors that are being used in tomorrow's vehicle. So modeling those sensors, having powerful simulation environments in which these models can be integrated together. So even people are talking about 3D objects in environmental models, control software and hardware models, modeling the complex road traffic. One of the issues that one has to take into account in this context is fidelity of the model, how faithful that the model is to reality. People are even talking about data-based models, essentially having a continuous interaction with the vehicles on the road, creating digital twins of that. This is something will become an important reality as over-the-air updates happen and there are several configurations that are there, different types of vehicles are there on the road, it may become necessary for having a digital representation of these vehicles, so that whenever changes are being made, so you need to track them. So if you look at on the right-hand side, a simple control loop, there are several control loops that are running in our vehicles. And if you look at each of those boxes, including the environment, all of them are being modeled and integrating them. So many of their tool vendors have started providing features, providing methodologies for creating models of the environment, and then running hundreds and thousands of simulations in order to validate your software changes. This is the kind of so several changes, transformations that are happening. And so my focus of research has been on validation. So system validation, even prior to these changes, major effort in development, 60 to 70%, for all estimates, divided into two major activities, verification and validation, as we would like to call it in this area. Verification involves checking whether the described requirements are met by the system. Whether the system is built right, whereas validation is talking about whether the right system is built or not. So there is always a gap between the intention and the extension, and this gap increases as we start building more complex systems. I will give you a pause here. So is there any questions, or Professor Chakrabarti? That so I hope that all of you are there.
So what I have done is invited the members of the audience to type out their questions in the chat boxes, and we would take them up at the end of your talk. This has been the tradition in Samvaad so far. But if you would like to take them up right away, that's your call to take, of course. Please feel free to do as you prefer. Or otherwise, we'll go with the traditional approach and take them up later.
Sure, that's fine. I think so. Let me go ahead, and then maybe we could have a kind of longer interaction session, right?
Yes, yes.
Okay. Thank you. So verification clearly follows the kind of what we call as a design hierarchy. Now you start with vehicle level requirements, which gets divided into subsystem requirements, and then subsystems to subsystems, and then up to the components and function requirements. System level requirements decomposed iteratively to subsystem and component requirements, and the overall verification task is divided into verification of components and subsystems. And then that gave rise to unit testing and integration testing. So what I am highlighting here is what has been traditionally happening. So component verification. So you can see on the right hand side, some of the kind of ISO standard 26262. It's a kind of very well known standard. Its recommendations for unit testing. So two major approaches like white box and black box testing. White box verification could be static analysis, formal verification, property-based verifications, and black box approaches like testing. Static analysis and testing is kind of widely used in the industry for component verification. And the major verification effort is involved in integration verification. As you can see on the right-hand side, there are the software that is involved in vehicles are having multiple control loops. So in-loop simulations or in-loop verification or validation is a lot of effort, and times are being spent, weeks and weeks of testing that are being used from multiple levels of integration, starting from model in the loop, which is less time consuming, and then early in the design and development cycle, one can do that, to software in loop, hardware in loop, plant in loop, and then complete vehicle in loop. So there's a whole variety of testing and validation activities that take place, starting from in the distributed software, individual controller level components to the multi-controller integration level validation that take place. So validation, so in contrast to verification is along the traditional lines, extensive on-road testing. So many of you might have heard of testing, especially in the autonomous vehicle context. So companies like Waymo, Tesla, and Cruise doing extensive on-road testing. Mostly vehicles are being used, or sometimes to be safe. There are incidents even during the testing process, accidents and so on. So safety during testing is also becoming seriously looked into. And so that's why the companies resort to closed course setting. So companies have GM, for example, has its own campus where it can have varieties of roads, varieties of traffics being simulated on their closed course setting, and then vehicles are being tested. Huge amount of data is collected and analyzed. Of course, the question is how much testing is enough. There are interesting reports. One of which I have just some table, interesting table that I have listed here on the safety of autonomous vehicles by Rand Corporation researchers. Really, they are talking about in order to reach the level of human driving capabilities. So one has to drive millions and millions of miles. How are we going to do that? And these millions of miles need to be driven without any accident, right? If there are any accidents during the testing, then you need to go and retest for another millions and millions of miles. So as a result, simulation is becoming an important piece. That's where I was talking about virtualization. So simulation as an enhancement, extensive set of base scenarios and variations are being simulated. I think this is a figure maybe a couple of years old. Waymo simulated 15 billion miles of driving. Cruise automation, for example, simulated 200,000 hours of driving per day. There are a whole lot of support for simulations like scenario description languages, scenarios describing the variety of scenarios that you see on the right-hand side, taking real life situations and then trying to simulate them in simulation languages, powerful simulation platforms, some of which I have written down: Vera's VTD, Virtual Test Drive, IPG Car Maker, Carla, even open source simulators, even many more are coming into the field. Now, these simulation platforms enable you to include your the ego vehicle, that's it, the vehicle under test being software being introduced, and then simulating the traffic, simulating the sensors, variety of the sensor models, and 3D object models can be simulated on this. Even there are extensive efforts on capturing naturalistic driving scenarios and then including them in some kind of real to virtual, right? Collect real data and then run real scenarios, and then introducing them into your simulation platforms, and then carry out variation studies and so on. Right, and the traditional challenges, several issues facing level 3+ systems. Perception capabilities, especially those being triggered or enabled by AI functionality, has several problems. And safety, functional safety, right? Safety under failure. This is one of the majorly studied effort. 26262 standard is one of the functional safety standards. And these standards are very much applicable for validating and developing level 3+ systems as well. One of the factors that affect validation of these systems is performance, right? Size of the systems are enormous. If you are talking about deep neural networks that are being used in these systems, they are DNNs of millions of parameters, and 50 layers are quite common, right? Some of the sensor manufacturers, camera manufacturers like Mobileye, incorporate these complex networks to identify objects and situations and so on. How are we going to validate them when their sizes are so large? Of course, there are many new novel challenges. So people talk about not only safety under failures, but insufficiency of perceptions. This is something very common even for human beings. Assessing the situations, avoiding collisions and so on, requires a lot more knowledge, right? Not only the mere perception of objects and events nearby, but you need to think about their intent. What could possibly happen in future? Some kind of replay of mental play of playing of those behaviors and so on. So insufficiency of the perception is being seriously taken into account. Edge cases that could be triggered by events. I think this is also another serious considerations. Some of the sensors are capable of performing under ideal conditions. Now suddenly there is a situation changes, like sudden burst of sunlight when you're going under a bridge, and there is a almost near darkness, and then when you come out of the bridge, there could be a sudden burst of sunlight. Then the behavior might change. These are called as edge cases, that are triggered by events. These need to be also looked into. And of course, another thing is misuse and misbehavior by traffic participants. Now we need to take into account not only the legal behaviors, but sometimes misbehaviors. One of the recent incidents that happened with cruise automation, some of you might have already heard about this. There was a month back or a couple of months back, what happened that when a cruise vehicle was trying to take a left turn, right? It was trying to take a left turn, and then there was a vehicle on the rightmost on the oncoming vehicle. Instead of taking the right turn, the vehicle, the cruise automation vehicle was thinking that the vehicle is going to take a right turn, but actually it changed its lane and then suddenly came straight. So these kinds of misbehaviors need to be predicted accurately, and then accordingly action need to be taken. So several new para-functional requirements, like explainability, trustworthiness. So what they call as black swan situation. You train your network with only with white swans, and then suddenly the black swan appears. How are you going to explain whether your system is capable of perceiving and assessing the situation and so on? Robustness is one of the important factors for next generation vehicle. So as I was talking about safety of the intended function, SOTIF, I think this new standard that has come out, which is called 21448. They introduced the concept of nominal safety or safety of the intended function, right? 26262 is one of the older standards. They were talking about safety under failures, right? When any subsystem fails, either due to random or systematic faults, how to take care of that, whether there are any safety, unsafe situations that arise, how do we take care of that? Systems need to be architected for those unsafe situations arising because of failures. Whereas in the case of 21448, this is a kind of new standard that have come out, as to take into account even nominal behaviors might introduce unsafe situations. So one has to think about, so even when you're studying, analyzing your requirements and developing, what are the possibilities of unsafe situations that might arise? One of the things that we talk about is perception insufficiency, ensure that there could be limitations of the sensors. How do we take into account, how do we understand, appreciate, and comprehend these limitations of sensors, and then take corrective actions on that. So if we look at looking at the kind of enormous challenges which are already there in today's vehicle, and then as we are introducing level 3+ vehicles, so verification and validation is not a kind of simple task. So you cannot have a black box approach of architecting your system and then feeding the system into a kind of verification engine, and then the verification engine can simply analyze and bring out the results, whether there are any faults or not. I think more a detective approach need to be followed for V&V. So essentially, the industry is trying to follow some kind of arguments and evidences for building a case for correctness. Now people talk about absence of unreasonable risk, right? I think these are explicit in safety validation in some of the safety standards. And some of the verification tasks, it is implicit. Now, for example, on the right-hand side, we have some classical ASPICE, automotive SPICE standards, which recommend various methods of uh, requirements, decompositions, hardware and software designs, and then the validation steps to be taken and so on. So the arguments emphasize well understood and accepted engineering practices, methods, and tools. They are mostly process focused. Standards and guidelines are there, and a host of intermediate development artifacts need to be produced, right? So I think so. Who decides the quality of? This is a kind of question, right? So it's not the end product alone you can examine. You need to examine all the intermediate products or intermediate artifacts. You need to look at the requirements, how the requirements were decomposed, what kind of test cases were exercised on the individual components, how the components were architected, and so on. A variety of V assets need to be provided by the supplier when they are supplying a product. So for safety assurance, as I said, 26262 and 2148, some of these standards are not adequate. They were defined or designed for level 2 systems. And some of the newer systems that are coming in level 3+ systems, these standards are being actually refined and redefined, some of which I am actually participating, and then I will give some details and as I move forward. Right. So there's a kind of an argument strategy that you need to employ when you're reasoning about the correctness or safety of these systems. So one has to distinguish the intention and extension as you do in verification and validation. And if you look at on the right-hand side, so we need to really decompose the requirements along different lines. You have functional requirements, you have safety requirements, you have security requirements, and a host of other requirements, even performance requirements, and so on. So, and then verifications and will be based upon explicit requirements. So safety engineering is a kind of very advanced field, coming from kind of aircraft and nuclear industries. Automotive industries have slowly embraced these safety engineering practices. Some of the standards that I talked about, 26262 and 21448, which are becoming a kind of common practice in the industry, follow this systematic process. A brief overview of that is given on the right-hand side. So it's a kind of some kind of a fault, systematic exploration of hazards and faults, and then tracing their origins, and then what kind of analysis one has to do, and then what kind of actions that need to be taken. So you talk about hazards and safety goals, and includes safety requirements as part of the functional requirements, and then assigning what they call as automotive safety integrity levels. Now people talk about ASL A, B, C, D, D being of the highest integrity level. So during the design, further refinement of these ASL requirements into technical safety requirements, various kinds of software analysis, and then software artifacts, additional artifacts that need to be introduced to take care of the faulty situations that might arise either due to random hardware failures or systematic software failures. And verification and validation involves essentially fault injection testing. So in order to check that whether your system is safe or not, you may have to simulate faults. And if there are multiple components are there, and then there is a kind of explosive combinations of different faults, this also increases the effort that are involved in verification and validation. And typically people talk about when before releasing a product, one has to create safety cases or safety arguments in a systematic way using the argumentative strategy that I talked about. So in the case of 21448, people talk about safety of the intended function. So it involves systematic identification of hazards caused by, not necessarily by failures, but caused by, this, one could think of them as systematic failures caused by limitations of sensors or insufficiencies of sensors and sensing. Even misuses need to be taken into account. When we say misuse, there could be a misunderstanding by the user, right? Now there's a kind of interaction between the user and the system. These are well-known problems of automation that the user might be expecting that the system is in control, whereas the system might be thinking that the user has taken over the control and so on. So one has to take into account these things. There could be known and unknown limitations. On the right-hand side, you can see that, of course, there are several unknown situations that might be there. How do we quantify, how do we take into account this unknown safety, unsafe situations? And I think this is one of the challenges in validations to look for these unknown limitations using long exposure testing. And then you release a vehicle only after you are sufficiently sure that these unknown limitations are as and when they crop up, you need to have you need to be agile in updating your software and so on. In some sense, nominal safety engineering has also given rise to this and enabled by connectivity over their updates and so on. Right, I think functionality in safety is tightly integrated. Every design step undergoes safety analysis, and then safety analysis leads to design iterations. Iteration and integration of functional safety and nominal safety need to be done. And V&V steps are expected to provide evidence of all the three concerns. And as I said, that additional assets need to be created, like safety requirements, PHA analysis, fault-free analysis results, and then safety cases need to be demonstrated before a vehicle can be released or before any update is. So as a result, there is a host of V&V assets, requirements, test cases, coverage data, verification plan, verification models, and they need to be maintained. Just like software, they need to be maintained and revision controlled. And more important in the agile area as things are being changing. Right, so completeness of verification is always a kind of concern. Coverage is a very standard metric for verification. Requirements coverage, code coverage, and so, but these are primarily used in the kind of unit testing. There are no good metrics for integration testing. And at least in the kind of individual control algorithm developments, one can use correct by construction, but ultimately for the end product, you need to have more rigorous methodologies for validation. Of course, so one of the issues, the V&V limitations, there are inherent limitations. Even if you are going to use a verification engine, who verifies the verifier? There's a kind of infinite rigors that are involved, infinite behaviors. And one of the issues that are becoming also more important is that systems are product lines. There are a huge number of configurations, field configurations that might arise, especially due to these recent changes like over-the-air updates and so on. And as multiple, often huge number of system configurations that exist in today's systems. If we take a GM-like company, GM has a whole line of product line, multiple products being architected, but they all have some kind of product line approach of common assets with kind of variations and so on. So when you talk about development of individual products, you cannot go and architect the entire system individually. You need to have a set of common assets. Architecture could be common, certain base software could be common, but the applications might be changing. As a result, when you are going to do verification and validation need to also take into account the structure that is available in product line, right? And then another features introduced by level 2+ features is that huge variability in the environment, right? beside the physical plant, your engines, and electric motors, there could be variations in that. Some of the assets could be used across, from ICE to especially application assets could be used across different engines and motors, but even the variations in environments. If you are going to talk about a lane lane keeping assist or lane change, right? Now imagine the variabilities that are going to occur. When you are going to talk about variations, verifications, you need to take into account variations of this, different ways in which different gaps that different users, different vehicles, the enormous amount of variation that exists. How are we going to validate that? Before releasing a vehicle or releasing a software, one has to take into account these variabilities. So the challenges of validating and then making sure that all these variabilities are nicely traversed or analyzed is an important issue. So the VNV of product lines assumes greater importance. How do we provide guarantee of all the products, right? Products are the individual instances of this product line. There could be exponential number of products, infinite number of environmental variations. So some of the solutions people talk about is lifting VNV methods from product to product lines, what they call as 150% product modeling. So essentially, instead of modeling one product, we model the entire product line. And tools and methodologies are in place. So for example, large-scale cloud-based simulations, design of experiments, statistical sampling, and then digital twins. These are some of the technologies that are being introduced. Essentially, take one product line, introduce variations, parametric variations, do some kind of parameter swapping, and then run multiple simulations on the cloud, and then look for any possible deviations in behaviors and so on. Right. I think that the other one is triggered by this new software-defined vehicle architecture. So we are talking about continuous VNV, right? So VNV, just like design is being continuously changed and revised, so one needs to do this continual VNV, continuous. So even more variability about the lifetime of a vehicle that might occur. For example, people are talking about subscription-based functionality, right? Every individual vehicle owner could ask for different features. So the vehicle A could differ from vehicle B because of these, the respective owners might have subscribed to different functionalities that might give rise to different variations or configurations. One has to validate, all those possible configurations. And it is becoming a kind of common feature of continuous monitoring of property violations on the field, and then looking for edge cases, new corner cases and edge cases, and then quickly reacting to these, and then creating and developing updates, and then modifying them will become commonplace going forward. So as far as the work that is concerned, so various new standardization activities that have started, industry-wide guidelines and standards for design and verification and validation of level 3+ system. It's an active area. Extension of 26262 and 21448 standards are being worked out. Some of the standards and past documents that are coming out. PIS 8800 is one of the document that's being prepared. Safety and AI. This is focusing on how do we ensure developing safety systems in the presence of AI and machine learning components. This is one of the standards I am participating in. There is an extension, one could say that extension of 26262 and 21448 ideas for safety and cybersecurity for automated road vehicles. These are essentially meant for level 3+ systems, level 3 and 4 systems primarily. This is a standard that's coming out. It's called TS 5083. I'm also participating in this standards. Uh, in, um, in addition to that, there is a US CAR organizations. I'm leading a work group on verification and validation of AI machine learning based components. On the right-hand side, you can see that we have released a second version of this document. All these are essentially trying to provide guidelines, methodologies for taking care of verification and validation issues, what additional metrics and measures one needs to define for taking care of the standards and challenges that I highlighted. We are also collaborating as part of our R&D work with several universities. We are focusing on product lines, right? Product line analysis, product line modeling, product line safety processes are some of the efforts that are currently underway, in which our group is participating. And with this, I would like to conclude my presentations. And here are the kind of talk highlights. And then I will give you a pass and then attend to your questions. And then maybe as part of the questions, I can elaborate some of these aspects. Thank you, Chakrabarti. Any questions?
Thank you, Dr. Ramesh. This was a very, very interesting and highly perspective talk to think about so many ideas, so many problems. It almost sounds overwhelming. To put it a little comically, it feels as if it's becoming more and more dangerous to drive a car. but also it's very exciting as far as computer science research is concerned. Yeah, this is very interesting. Thank you for the talk. And what we have today here is a small but very, very engaged audience. And that is demonstrated by the number of questions that we have got in the chat box. So I
Thank you. Right. I think not just before answering those, of course, I think I could give, given a kind of 40 minutes to 1 hour, I think there are interesting developments, and then there's a whole course on automotive software systems and verification and validation. Individual courses, semester-long courses, that we need to run in order to elaborate. So I try to squeeze in and then just highlight the challenges and then possible areas of research.
Very nice. In fact, I had one question in that regard, so I will really get in touch with you later on. So let us first give preference to the questions from the audiences, and I would like to invite the respective questioners, askers of the questions to present their questions. So Professor Roland, yours was the first question. Can we have it from you? Do you speak it out?
Sure, yes. First of all, thank you very much for that very inspiring talk. And you did a fantastic job to squeeze a lot of this information into a format of about 50 minutes or so. Question I had that was about the models. You talked about different models, vehicle models, combustion engine models, and also battery models. Now, on the combustion engine side and vehicle models, the auto industry has had decades of modeling and improving these models. And now with the transformation towards e-mobility, battery models are very important, of course. How would you or how would you compare the quality, the depth of the battery models compared to the other models the industry uses, like vehicle control system models or the combustion engine models? Is it on the same level or still a lot to be done so that the battery models that are being used would be on the same level of accuracy and confidentiality we can have in these models precision of these models have compared to the other models?
Very interesting and important question. Thank you for asking that. Unfortunately, that I don't work in this area. I'm sure that some of these models are advanced enough, as they are releasing, many of the simulation studies are being done using these models. I'm sure that they are at a kind of at a stage mature enough to be, for the product to be released and so on. But there could be a lot more, that may be required. But unfortunately, that I don't work in this area, but it's an important question.
Okay, thanks.
So Srishti has many questions from her side. What I can do is, first of all, commend her for being so engaged and interested. Thank you. But due to paucity of time, I will probably have to request you to ask one or two of your top questions, and the rest of them can be asked maybe over an email.
Yeah, fine. I think only ones which are highlighted in the top, and then it follows to the rest.
Okay, please go ahead and ask it, Rosa.
So I wanted to also understand, so I just read out the question. In context of SDV, how far can this address the vehicle features or requirements? For example, there are many real-time requirements and constraints. So maybe usability or features can be imagined as apps bringing in flexibility through the SDV. So can you just mention, like, how do I visualize that, to what extent SDV can really complement?
Okay, so thank you, Srishti, for these questions. Feel free to reach out to me for other questions. My email is there, and then I would be happy to answer many of those questions. Right, I think these are some of the very important topics, right? How are we going to achieve real-time requirements using these app-based extensions and so on, right? Now, currently, if you see that in order for predictability, most of the practices, industry practices, automotive system being a kind of deeply embedded real-time systems, the real-time capabilities are achieved through extensive way of architecting them, taking care of predictability as one of the important features. Now we need to see that as new apps are being included, how are we going to do that? These are very important questions. So currently, the apps are being introduced in the kind of non-real-time space. But the desire is to actually bring it to even look at your engine control system or battery management system. So they need to be also as imagined as having a kind of set of services and apps. And then when the apps are getting changed, so you need to have, you need to maintain the same kind of real-time requirements, if not more. This is a kind of a research question, I would say, right? So
actually, so why this question is because, like you said, these vehicles as a unit is a deeply embedded system. So that means most of the requirements then fall in the category of, let's say, real-time constraints. And now we are talking about SDV. So as we make the layers of the software which runs on these systems, we are actually kind of adding some sort of latency or processing time in there. So we are actually bringing in certain flexibility with this SDV, but we are also adding some time to it. So I'm just trying to understand that to what extent can I visualize SDV solving the problem of the vehicle space? And also there would be, I feel, some set which is not addressable by the SDV. So maybe something else has to be there. So that's just my thought. I wanted to have your opinion also.
No, I think that's a very important point that you highlighted, that SDV, software defined vehicle, is a kind of industry need. People want to develop and then bring out functionality in a kind of agile fashion, but it's going to impose severe challenges for automotive systems, right? So I think one of the ways in which it's being responded to by having this shift from the regular AutoSAR to adaptive AutoSAR. So you need to have some kind of dynamic scheduling policies and so on into the vehicle. So I think that is one of the issues, how to bring in predictability, under the case of dynamic scheduling, giving some high priorities and then deadlines for some of these apps and features. right? So there are real-time solutions, real-time, deeply embedded solutions for in the dynamic space. Some of those ideas need to be, brought in here. Identifying a small class of apps and services that need to be given high priority, right? As and when they arise, they need to be given priority. So enough resources are available, so allocating resources for these high priority tasks, and then dynamically switching your scheduling strategy and so on. These are some of the solutions, but more need to be done, right? So one has to do kind of modeling and then ensure that real-time requirements are met and so on.
Okay. Just in continuation to this other question which I posted was that how close is the validation to the real system? Because software running on PC and software running on, let's say, controller or processor in vehicle would differ. How is this approached in the validation?
Right. I think one of the ways in which this is being approached is modeling them, right?
Mm-hmm.
So you have appropriate models for the various, some of which I think Professor Roland was talking about, like simulating, right, the vehicle behavior, simulating any of the actuators and the plants that are being controlled, simulating your environment, and then including them as part of your validation efforts. So as a result, even though your software control might be small, you need to include the models of your environment, models of your so actuators and plans in order to do the validation.
So models, I understand that it will be kind of an extract that how it would behave. But let's say I have a end software which has to go and run on the vehicle. Now, this piece of software will actually be having a different hardware altogether underneath, right? And it's been written for that software, customized for that software. Now, but then if I have to validate, let's say on a PC setup, that's entirely different. So we cannot really expect that it would behave the same way when it is actually in a different, because that's a very significant variable which is going to change. For example,
right. I think, okay, so I got your question. So I think I have just flashed this slide. I think that is one of the reasons why these multiple levels of in-loop simulations that are being carried out, right? So for example, MIL, it's in the modeling space. You can use MathWorks like modeling tools, and then here you model everything in your modeling language, favorite modeling language, and then do in-loop simulations of the model. Then you have next level software in loop, where the source code of the software that's being developed is being tested. And then finally, when you talk about Hill, for example, hardware in the loop, here actually the target code is being tested. So essentially, the kind of things that you talked about is that what is running on your PC could be that here it's only the application functionality is being tested in the software in loop, whereas in the hardware in loop, there are simulation facilities that are available where you go and actually flash your software onto the controller and then include the controller in the validation, right? So what is being tested is the final target code rather than the source code.
So this Hill that you're mentioning here is essentially for putting that software code into a, let's say, several loops and testing it, but not validating on, let's say, a functional subset of it. No, not that way. That's how
I think it is. So I think one of the questions you asked is that from PC environment, how do you go to the target environment? Here, actually, this I have just given a kind of iconized version of this. Now this is actually a D-space Hill box, which can accommodate. You have slots for putting your own controller, and then flashing your controller into that control hardware. And then flashing your, recompiling your software into the target hardware, and then keeping it in the loop.
So this is essentially equivalent to that hardware which is sitting in the vehicle.
It is the
right?
same hardware. Inside,
Okay.
it is the same hardware. So I just showed only one picture. There could be multiple such hill platforms which are being integrated together. Entire network is connected, right? So they are connected to the CAN buses and Ethernets, and then connecting them together. And then what you're exciting is what could happen in the real vehicle.
Understood. Yeah.
Good question. Very good question.
Thank you,
sir. That's all
Srishti.
for now.
Thank you for the very good questions. The next question is from Sai Pradeep. Sai Pradeep, if you are there, maybe you would like to speak up.
Sure, sir. Sir, my question is, like once we put these models into production, how often are the models updated? Like after the final deployment into the production, how are things updated? How is the software updated? How is data? How is the feedback coming up? So what is the life cycle behind this post-production maintenance? Just can you provide your insights in this matter?
Right. I think these are, I think it's OEM, the company dependent. I have heard from our company that, so again, this depends upon the behavior of these models. So I think every quarterly updates have become very commonplace these days. And of course, if there are any debugging or any important issues, then it is being, this updation takes place immediately, right? Depending upon the kind of safety situations and so on. But otherwise, currently they are talking about quarterly updates and all the controllers that are there on the vehicle, they can be subjected to updates.
So
thanks for your question. I think it's interesting.
Yes, thanks. So such models, can we have an understanding that data is continuously shared at some cloud level? I mean, from the vehicle.
Exactly.
Okay.
Yeah, exactly. Right. There are, for new features, for example, it is becoming a kind of common aspect these days is to continuously monitor and collect data. Based upon the collections, you can do analysis, post-processing analysis. There's a kind of whole IT infrastructure that is in place for cloud-based analysis. And so on.
Understood, sir. Thank you very much.
Thank you, Sai Pradeep. The next question is from our colleague, Professor Meenakshi D'Souza. Meenakshi, are you there? Could you ask your question?
Yeah, thanks, Sujit. Thanks, Professor Ramesh. Nice to see you online and hear your good talk. So I just had this question related to, you were talking about there being very good modeling simulation tools available, the Carla simulator and other things that you were talking about. My question was related to, so increasingly, I mean, they are considering the use of these perception and other prediction algorithms for various tasks in autonomous driving. And if you see the papers that talk about these formal methods, the model starts with the simulator. It doesn't start with the system. So is there any work that talks about the using the data along with these simulators for these kinds of tasks, perception related tasks? Or?
Good question, Glenn. Glad to talk to you, Meenakshi. If you are talking about any papers that are
I'm aware of papers that use simulator data, simulators for perception. My question was, the automotive simulators, do they also provide data that can be used by, that can be fed on to, let's say, a CNN with some processing to do perception related tasks?
Right. So these are at the kind of, I would say that at the production level, there might be something that might be happening. But currently, if you see, if you look at the current situation, that most of these DNNs are being the supplier driven, right? So typically these DNNs and perception tasks, many of them are come integrated with suppliers, right? Mobileye, for example, furnishes cameras which have these DNN tasks. So as a result, so it all depends upon the agreement between the supplier and the OEMs. Currently, that the OEM data remains with the OEMs. There are some discrepancies at the feature level are being monitored, and if they are traced back to the kind of perception subsystem, then this data is being shared with the suppliers, so that the suppliers can go and and look at it. And this is one of the things that we are talking about in some of the standards, is to how do we take this, highlight the processes involved in the development and then revision of these DNNs based upon online data, right? I think this is one of the important features, but today it's being done restricted to the individual groups or individual suppliers who deliver these features. They are using this data to revise, but what processes that they use, that's unclear.
Okay.
Because it's something internal or proprietary.
Okay.
But it's a kind of very important aspect that this aspect is being considered seriously in some of the new standards that are coming in, like that I talked about.
Yeah. Okay. Thanks, Professor.
Okay. Thank you, Meenakshi, for your question. So now, in the interest of time, let's allow just one more question. This is from Tirthankar Banerjee. Tirthankar, are you there? Could you ask your question?
Yeah, sure. Thanks. Can you hear me?
Yes, yes.
Yes.
Okay. Thanks, Professor Srijit, and thanks, Dr. Ramesh, for a wonderful, insightful presentation. So my question is essentially, I wanted to understand that are all these simulations also considering the Indian road conditions, like typically a cycle, an auto rickshaw, or a cow pulled vehicle, things like that, because in most of the cities in India, it's like that even now. So is there any in the standards body, something which is not generally seen worldwide, but so in some of the third world countries and also in India? So are these also considered when we develop the safety standards or the simulation algorithms?
Yes. Good question. Thanks for asking this. And so when we talk about this in these standards, right? So these standards are so typically not monitored is not the word, administered by ISO, so in which experts from all over the world, including so for example China and Asian countries, people get involved. And when we talk about automated driving and objects, 3D objects on the road and so on, so we are expected to take into account all of them. Of course, there could be several challenges. There could be requirements on how clear the lane markings are. Those are also some of the important. Leave alone the kind of different variety of objects that you talked about. So even lane marking, right? How clear those lane markings need to be, and how much driving has taken place with degradations in lane markers and so on. So the answer is yes, we need to take into account when we go and talk about. But of course, what they might happen is that some of the kind of initial versions of that, the ODD themselves might go and dictate and limit the usage of this, right? That the ODD, one of the things that might say is that the condition should be appropriate enough, right? That the camera, for example, should be able to perceive, right? And in which case, typically that handover might happen, right? So in some sense, the standards will apply those. But the question that you're asking is that whether by applying these standards, whether automated driving subsystems can handle the situation or not, that's a different question, right? The standards will say that these are the things, these are the ground rules when ADS can take control, it might say. And when the situations are degrading or something, ADS might give over to the human. So as a result, the question is essentially directed to how often that ADS will be in control, right? In situations that you are describing is an important question, right? The standards typically don't address those. Does that answer your question?
Yes, thanks. It did. Thank you.
Right. Thank you.
Thank you, Tirthankar, for that question. And that brings us to the conclusion of this particular session. And in order to formally conclude it, let me thank our speaker today, Dr. Ramesh, for giving this very insightful and perspective type talk. Opened up so many questions and very exciting area of research for computer scientists, AI, ML enthusiasts. Also, special thanks for joining us at this wee hour. I know that it's early morning at your place. So thanks, additional thanks for that. I would also like to thank all the people in the audience. Thanks for joining in at this late evening hour. This was the best we could have done, considering the time zone differences. It was a very engaging talk. We had a very engaged audience too, though small. And I hope we continue our discussions. The questions I left out in the chat box, I'll try to copy them and pass them over to Dr. Ramesh, and hopefully he will have time to address some of them, and I will pass the answers to you subsequently. So thank you everyone, and have a good evening.